Welcome! Today we're diving into problem number 2189, sort the students by their KTH score. In this problem, we'll explore how to sort students based on their scores in a specific subject, which challenges us to think about sorting techniques and custom comparators. Let's get started. In this problem, we are given a 2D integer array called score, where each row represents the scores of a student in multiple subjects, and each column corresponds to a specific subject. Our goal is to sort the rows of this array in non-increasing order based on the scores in a specific column, which we refer to as the KTH subject. The input includes the score array, with dimensions mxn, where m is the number of students and n is the number of subjects, as well as an integer k that specifies the column index for sorting. The output is the rearranged score array, sorted according to the values in the KTH column in descending order. For example, consider the input where score is a 2D array containing the rows 10, 6, 9, 1, 7, 5, 11, 2, and 4, 8, 3, 15, and k is 2. Here, k equals 2 means we are sorting based on the third column. After sorting the rows by the values in this column in non-increasing order, the output becomes a new array with the rows rearranged as 7, 5, 11, 2, 10, 6, 9, 1, and 4, 8, 3, 15. Let's break this process down step by step. First, we identify the values in the KTH column, which in this case is the third column. These values are 9, 11, and 3. Sorting these values in non-increasing order gives us 11, 9, and 3. Next, we rearrange the rows of the score array to correspond to this sorted order. The row with the value 11 in the KTH column is 7, 5, 11, 2, followed by the row with 9, 10, 6, 9, 1, and finally the row with 3, 4, 8, 3, 15. As a result, the output array is 7, 5, 11, 2, 10, 6, 9, 1, 4, 8, 3, 15. In another example, consider the input score array 3, 4, 5, 6, and k equals 0. Here, k equals 0 means we are sorting based on the first column. The values in this column are 3 and 5. When sorted in non-increasing order, we get 5 followed by 3. Rearranging the rows accordingly, the row with 5 in the first column is 5, 6, and the row with 3 is 3, 4. Therefore, the output is 5, 6, 3, 4. Now let's look at a third example. Suppose the input score array is 1, 2, 3, 3, 2, 1, and k equals 1. Here, k equals 1 indicates that we are sorting based on the second column. The values in this column are both 2. Since the values in the KTH column are identical, the order of the rows remains unchanged. Thus, the output is 1, 2, 3, 3, 2, 1. In this example, we sorted based on a column where all values were the same, which led to no changes in the row order. This behavior highlights that when there is a tie in the values of the KTH column, we preserve the relative order of the rows as they appear in the input. Now, let's consider the constraints and edge cases for this problem. The constraints specify that the number of students, m, and the number of subjects, n, both lie between 1 and 250. Each score in the score array is a non-negative integer ranging from 0 to 100,000. The column index k is guaranteed to be valid, meaning it satisfies 0 equals k less than n. For edge cases, if there is only one student, the array does not change since there is only one row to sort. Similarly, if there is only one subject, sorting is unnecessary as there is only one column. Finally, if all values in the KTH column are identical, the order of rows remains unchanged. These scenarios ensure the solution handles special cases appropriately. To solve the problem of sorting students by their KTH score, several approaches can be considered. The simplest and most intuitive method is to use a brute force approach by leveraging Python's built-in sorted function or an equivalent in other programming languages. The idea here is to sort the rows of the score array based on the KTH column value in descending order. This can be achieved by passing a custom lambda function to the key parameter of sorted, which extracts the KTH score for comparison. Additionally, setting the reverse parameter to true ensures the sorting is done in descending order. The time complexity of this approach is O, n asterisk log n, which comes from the sorting operation, and the space complexity is O, n, due to the additional memory required for sorting. One of the key advantages of this approach is that it leverages highly optimized built-in sorting algorithms, making it both efficient and straightforward to implement for moderately sized datasets. Another approach involves manually implementing a sorting algorithm, such as quicksort or merge sort, and customizing it to sort based on the KTH column. Here, the sorting logic is determined by using the KTH score as the pivot for comparisons. This requires writing a dedicated sorting function that carefully handles the descending order requirement. While the time complexity remains O (n asterisk log n) for efficient algorithms like quicksort or merge sort, the space complexity depends on the choice of the algorithm, for example, O log n for quicksort due to recursion or O n for merge sort. One important observation is that avoiding library functions can be beneficial in constrained environments where external utilities are unavailable. However, this approach has its downsides, including increased complexity, being more error-prone, and requiring extra effort to implement correctly. For larger or more complex datasets, relying on manual sorting may not be as practical as built-in solutions. For situations where the KTH scores are bounded within a small range, an alternative approach is to use counting sort, a non-comparison-based sorting algorithm. This method is particularly efficient since it groups the students based on their KTH score and then iterates through the scores in descending order to construct the final sorted array. The time complexity of this approach is O (n plus r), where r is the range of possible scores, and its space complexity is also O (n plus r). This makes counting sort exceptionally fast for cases with small, bounded ranges. However, it is less flexible than comparison-based sorting algorithms. For instance, it cannot handle unbounded or non-integer scores, which limits its applicability in scenarios where the KTH column values do not meet these conditions. While this approach can provide substantial performance benefits under the right constraints, it is not a one-size-fits-all solution. After evaluating different methods, the optimized approach we chose is to use built-in sorting with a custom key. This decision was made because it strikes the best balance between simplicity, efficiency, and flexibility. The brute force approach using Python sorted function is easy to implement and works well for a wide range of input sizes and score ranges. The process involves using a lambda function as the sorting key to extract the KTH column value and setting the reverse parameter to true to ensure descending order. This method avoids the complexity of manual sorting and works seamlessly for both integer and floating point scores. While it relies on library functions, which might be a limitation in certain constrained environments, the trade-offs are minimal for typical use cases. It provides an efficient O (n asterisk log n) time complexity and remains widely applicable across different datasets. In terms of final complexity, this chosen approach offers a time complexity of O (n asterisk log n) due to the sorting operation and a space complexity of O (n) because of the additional memory required for sorting. These characteristics make it the optimal solution when factoring in simplicity, efficiency, and flexibility. Among the various strategies considered, this approach stands out as the best trade-off, handling larger datasets effectively while maintaining ease of implementation. It is robust enough for a wide range of scenarios, making it a highly practical choice for solving the problem of sorting students by their KTH score. In this problem, we need to sort a 2D array of student scores based on their scores in a specific subject, identified by an index k. Each row in this 2D array represents a student's scores across multiple subjects, while each column represents scores for a particular subject. Our goal is to sort these rows in descending order of the scores in the KTH column. For example, if the input array is a 3x3 matrix and k equals 1, we're sorting by the second column of scores. The output should be a new 2D array with the rows rearranged so that the KTH column is sorted in descending order. To achieve this, we'll use a sorting algorithm with a custom key that focuses on the KTH column specifically. This approach allows us to efficiently isolate the column of interest while keeping the logic concise and readable. To break the algorithm into steps, the first task is to define the sorting key. This key will determine the order of the rows based on the values in the KTH column. For instance, if k equals 1, the sorting key for each row would be the value at index 1. So, for the rows 90, 80, 70, 85, 95, 60, and 75, 85, 95, the keys would be 80, 95, and 85, respectively. To sort these values in descending order, we can use Python sorted function with the reverse equals true argument. This ensures that the rows with higher KTH column values appear first. The sorting operation itself has a time complexity of O, n asterisk log, n, making it efficient even for a large number of students. Finally, after sorting, we return the resulting 2D array. It's also important to handle edge cases, such as when the input array is empty or when the value of k is invalid, like being out of bounds for the number of columns. One important aspect to address is what happens when multiple rows have the same value in the kth column. In such cases, the relative order of these rows should remain the same as in the original input. This property is known as stability, and Python's sorted function is stable by default. This means that for rows with equal values in the kth column, their positions relative to each other will not change after sorting. Additionally, Python's sorted function supports custom key functions, which makes it straightforward to sort by any column. By using the reverse equals true parameter, we can achieve descending order without any extra computation. The algorithm is efficient, leveraging timsort with a time complexity of O, n asterisk log, n, making it well suited for large datasets. Finally, the use of a 2D list is ideal for this problem since it naturally represents a table of student scores, allowing us to easily access and manipulate rows and columns as needed. The implementation of the algorithm is both concise and efficient. We start by defining the input array of scores and the index k for the column we want to sort by. Using Python's sorted function, we pass a lambda function as the key. This lambda function extracts the value in the kth column for each row. By setting the reverse equals true parameter, we ensure that the rows are sorted in descending order of the kth column values. The function then returns the sorted array. For example, given the input array 90, 80, 70, 85, 95, 60, 75, 85, 95, and k equals 1, the sorting process will rearrange the rows so that the second column appears in descending order. The time complexity of this operation is O, n asterisk log, n, due to the sorting step, and the space complexity is O, n, for storing the sorted output. To illustrate the sorting process step by step, we first extract the values from the kth column, which in this case are 80, 95, 85. Next, these values are sorted in descending order, resulting in 95, 85, 80. Based on this order, we rearrange the rows of the input array to produce the final sorted array 85, 95, 60, 75, 85, 95, 90, 80, 70. This output meets the requirements of sorting by the kth column in descending order while maintaining the stability of rows with equal values. This example highlights how the algorithm efficiently organizes the data using Python's built-in sorting functionality, providing both clarity and performance. The provided solution solves LeetCode problem number 2189, sort the students by their kth score. The task requires sorting a 2D list of student scores based on the kth column, which represents the scores of a specific subject. The sorting must occur in descending order. The method sort the students is implemented as part of the solution class. It takes two arguments, scores, a 2D list of integers representing student scores, and k, an integer indicating the column index to sort by. The core of the solution uses Python's built-in sorted function. The key parameter is used to specify that sorting should be performed based on the scores in the kth column. A lambda function lambda xx, k, is passed to the key parameter, which extracts the kth element from each row for comparison. The reverse equals true argument ensures that sorting is performed in descending order, as required by the problem. This approach is both concise and efficient. The sorted function has a time complexity of O, n asterisk log, n, where n is the number of students, rows in the 2D list. This ensures the solution is scalable for large inputs. Since the function directly returns the sorted list, it does not modify the original input, adhering to functional programming principles. This makes the implementation clean, reliable, and easy to understand. Overall, the solution leverages Python's powerful built-in capabilities for sorting and is tailored precisely to meet the problem's requirements. This is the Java implementation of the sort the students by their kth score problem from LeetCode. The logic mirrors the Python implementation using Java-specific constructs. Here, the 2D array is converted to a list for sorting, and the comparator is used to sort based on the kth column in descending order. The sorted list is then converted back to a 2D array before being returned. In this example, we are given a list of students' scores, where each student has scores in multiple subjects. The variable scores represents this data, and the value of k is 1, meaning we need to sort the students based on their scores in the second subject, which corresponds to the column at index 1. To achieve this, the sorted function is used, and we specify the sorting key as lambda xx, k. This lambda function extracts the score at the kth index for each student, allowing us to sort by the desired column. The sorting process evaluates the lambda function for each student to determine the sorting key. For the first student, 90, 80, 70, the lambda function returns 80. For the second student, 85, 95, 60, it returns 95. Finally, for the third student, 78, 88, 98, it returns 88. Since the reverse equals true parameter is set, the sorted function arranges the scores in descending order. This results in the final sorted list: 85, 95, 60, 78, 88, 98, 90, 80, 70. The output matches the sorted list, showing the students ordered by their second subject's score from highest to lowest. In this edge case, all students have identical scores across all subjects, as shown in the scores list. The value of k is 2, meaning we need to sort students based on the scores in the third subject, which is at index 2. When the sorted function is applied with the lambda key, it evaluates the score for the third subject for each student. Since these scores are identical, the sorting process does not change the order of the students. The lambda function evaluates the kth score for each student. For all students in this case, 50, 60, 70, the lambda function consistently returns 70, as they all have the same score in the third subject. Because all the sorting keys are equal, the sorted function retains the original order of the scores list. The final sorted list remains unchanged: 50, 60, 70, 50, 60, 70, 50, 60, 70. This demonstrates how the sorting algorithm behaves in scenarios where all the values in the sorting column are identical. Here, we have a larger dataset with 4 students, each having distinct scores in multiple subjects. The value of k is 0, so we are sorting the students based on their scores in the first subject, located at index 0. The lambda function evaluates the first score for each student. For the first student, 33, 55, 77, it returns 33. For the second student, 22, 99, 88, it returns 22. The process continues for the remaining students, determining the sorting keys based on the first subject's scores. The lambda function evaluates the first subject's score for the remaining students. For 11, 44, 66, it returns 11, and for 55, 33, 22, it returns 55. Once all the sorting keys are determined, the sorted function arranges these scores in descending order because of the reverse equals true parameter. The result is the order 55, 33, 22, 11. Using this order, the final sorted list is 55, 33, 22, 33, 55, 77, 22, 99, 88, 11, 44, 66. This output reflects the students sorted by their first subject scores from highest to lowest. In this problem, we're sorting a 2D list of student scores based on the values in the kth column, and we need to evaluate the time complexity of this operation. First, consider the dimensions of the input. The list scores has n rows, where each row represents a student, and m columns, representing the subjects. The sorting operation is performed using Python's built-in sorted function, which employs the timsort algorithm. Timsort has a time complexity of O, n asterisk log, n, for sorting a list of n elements. Additionally, the key function, which is a lambda function extracting the kth column value, is invoked once for each row. However, since the key function operates in constant time, its contribution of O, n, is negligible compared to the O, n asterisk log, n, cost of sorting. Therefore, the overall time complexity of the sorting step is dominated by the timsort algorithm, which is O, n asterisk log, n. Now let's analyze the space complexity of the code. The space usage comes from two sources: the auxiliary space required by the sorting algorithm and the memory allocated for the output. Timsort, the algorithm used by Python's sorted function, requires O, n, additional space to perform the sorting. Furthermore, the sorted function creates a new list to store the sorted rows, which requires O and *m space since the input scores contains n rows, each with m columns. When we combine these, the dominant factor in space usage is the output list, which leads to an overall space complexity of O and *m. This is because the auxiliary space for timsort, O, n, is relatively small in comparison to the space needed for the sorted output. Now let's consider the best, average, and worst-case scenarios for the time complexity. In the best case, where the rows are already sorted, the sorting algorithm still goes through the process of verifying the order, so the time complexity remains O and log n. In the average case, the behavior of timsort also results in O and log n, as the algorithm efficiently handles partially sorted data. Similarly, in the worst case, such as when the rows are in reverse order, the complexity does not change, remaining O and log n. Comparing this to a naive approach, where we might manually iterate through the list multiple times to sort, the naive method could involve complexities of O n squared, or worse, depending on the implementation. The current solution is highly optimized as it leverages timsort's efficiency and achieves the optimal complexity of O and log n. This is supported by the mathematical lower bound for comparison-based sorting algorithms, which proves that no comparison-based method can achieve better than O and log n in the average case. Therefore, the derived complexity is both tight and optimal for this problem. Let's start with some common mistakes that students encounter while solving sorting problems like this. First, misunderstanding the problem requirements is a frequent issue. For example, not paying attention to whether the task specifies sorting in ascending or descending order, or misinterpreting which criteria to prioritize, can lead to completely incorrect outputs. Sorting incorrectly becomes especially problematic when multiple criteria or constraints are involved. Next, we have inefficient sorting for large datasets. When handling a significant number of elements, using a nested loop approach with O n squared, complexity is a common pitfall. This method does not scale well for larger inputs, such as n greater than 10,000, and can result in timeouts during competitive programming or interviews. Lastly, failing to handle ties correctly is another critical error. If you ignore secondary or tertiary criteria to break ties, your solution may violate the problem's constraints and produce partial or incorrect results. This is why understanding the prioritization rules in the problem is so crucial. Another common mistake is not accounting for zero-based versus one-based indexing. Misinterpreting whether the KTH subject or element starts from index 0 or 1 can lead to off-by-one errors, which entirely shift the solution's output. These errors are subtle but can be devastating to your final result. Additionally, watch out for unintentionally mutating the original input. For example, sorting the input data in place when the problem expects you to return a new list can cause side effects. This is especially problematic in scenarios where the input data must remain intact for further use. Always ensure you create a copy of the data when necessary to avoid these unintended modifications. Now, when you're solving sorting problems in an interview setting, there are a few key things to keep in mind. First, always communicate your thought process clearly. Explain why you chose a specific sorting technique, especially if you're using a custom comparator or a lambda function. This helps the interviewer understand your reasoning and problem-solving approach. Next, edge case analysis is critical. Make sure you test cases like empty lists, single-element lists, or lists where all the scores are identical. Optimization is another important aspect. If the interviewer challenges you to come up with a more efficient solution, be prepared to discuss trade-offs between using built-in sorting functions with O n log n complexity and implementing more complex custom algorithms. Leverage library functions whenever possible, such as Python sorted or Java's collections.sort, as these simplify implementation. However, you should also be ready to write a custom comparator if the problem demands it. Lastly, think about space complexity. If the question specifies in-place sorting, explain how you would modify your solution to avoid using additional auxiliary space. Sorting problems like this are closely related to other challenges you'll encounter on platforms like LeetCode. For instance, in problem 973, k closest points to origin, you use sorting and custom comparators to identify the closest points to the origin. Similarly, in problem 451, sort characters by frequency, the task involves sorting characters based on frequency, which requires careful prioritization of criteria. Problem 658, find k closest elements, focuses on sorting and prioritizing based on proximity to a target value, while problem 1086, high-5, requires sorting student scores to aggregate the top k results. These related problems share common themes, such as custom sorting logic and the need to handle ties, making them excellent practice for mastering this topic. Finally, let's discuss some alternative approaches and their trade-offs. A brute force method using nested loops is simple to write but comes with a major drawback: its O(n)² complexity makes it inefficient for large datasets. This approach is best suited for small inputs or when constraints are lenient. Using built-in sorting with a custom key is a more efficient option, offering O(n log n) complexity and ease of implementation. However, it may require additional space for the sorted output, so it's ideal in scenarios where in-place sorting is not explicitly required. If you're only interested in a subset of the sorted results, such as the top k elements, a heap-based selection approach can reduce the time complexity to O(k log n), though it does require extra space. Lastly, implementing merge sort or quick sort variants provides flexibility for creating custom comparators, but this requires more effort compared to using built-in utilities. These alternatives are particularly useful in environments where robust sorting functions are unavailable or for educational purposes to deepen your understanding of sorting algorithms. Great job! In summary, we tackled sorting students by a specific subject score using a straightforward sorting approach with a custom key. This problem highlighted the importance of understanding sorting functions and custom comparators. Thanks for joining today, and I'll see you in the next problem walkthrough. Don't forget to subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!